Let's talk about exponential rules. Now, I think most of you have seen the rules and you know how to use them, but nevertheless, I want you to have some patience and listen to the entire lecture, because what I'm trying to do is not only show you the rules but also explain to you why these rules hold. That's because many students have this misconception that math rules are somehow randomly imposed on them, as if there's like a math king somewhere out there that would decree that here's the rule, everybody should follow this. Unfortunately, or fortunately, we don't have math kings, and all the rules are actually there because they have reasons. And if you know the reasons, then it's easier to remember them, it's easier to use them, and when you just memorize formulas, it's really easy to get confused, right? But knowing the reasons why those formulas hold can help you to remember the correct formulas. So it's very important that not only you know the rules themselves, but also know the reasons why. Okay, so here's the first one. A to the mth power times a to the nth power is a to the m plus n. And if I ask something like 2 to the third power times 2 to the fourth is equal to, times this is 2 to the 3 plus 4 is 7. And if I ask students, why does this hold? And most people will say, that's because this rule holds. And then if I ask, why does this rule hold? Then they would be like lost. What do you mean, right? Well, there's a reason why this is true. This is true because 2 to the third power means 2 times 2 times 2. 2 to the fourth power means 2 times 2 times 2 times 2, right? So how many times did you multiply 2? You multiply it a total of 7 times, right? So this actually helps you to understand why this rule is true. It just means that if you write a m times and then a n times, how many times did you write a? You've written it m plus n times. That's all it is. Here's another one. A to the mth power to the nth power equals to a to the m times n. And suppose you had like c squared and the third power. This rule would say that that's c to the sixth power. But why is that true? Again, if I press on and ask why this rule is true, many students won't be able to explain it. But if you just use the fact that powers, exponents, are repeated multiplication, it becomes all clear, because c squared is what? C times c, isn't it? And this cube means c times c is multiplied to itself 3 times, right? And how many times did you multiply c in all then? It's 1, 2, 3, 4, 5, 6, so it's c to the 6th power. Now there's a reason why I use c. It's because you can think of cookies as c. Okay, so let's say you have a bag of cookies, but each bag only has 2 cookies. And you have 3 such bags. How many cookies do you have in all? You multiply them, right? 2 times 3, that's 6. So if you think of A as some shape of a cookie, letter A shaped cookie, then this formula here has an obvious proof which says if you have m cookies per bag, this parenthesis, think of this as bag, and you have n such bags, how many cookies do you have in all? You have m times n cookies. That's what it is. All right, the next one is, what happens if you divide? Then you have to subtract. And for this, it's good to have an example of, say, a to the 5th power over a squared. And again, the proof is just writing out these exponents by their definition, which is a repeated multiplication. So a to the 5th means you repeatedly multiply a total of 5 times, and then a squared means you repeatedly multiply a twice. And once you do that, then you see that there's a here, there's a here, they cancel. This a and this a will cancel. So if you have 2 a's in the denominator, 2 on the top will cancel with it, leaving you only 3 left. So that's why you end up with a to the third. So again, the proof of this would be like if you have m a's and you delete n of them, erase n of them, what's left will be m minus n such a. That's the proof. All right, starting with D, the rules are not so straightforward. It's rather an extension of previous rules. And let me explain by writing out the rule first. A to the 0th power is 1. This is a rather strange thing to do because so far we've been using the fact that powers, exponents, are repeated multiplication, right? But what does it mean to multiply a 0 times? Does it even have a meaning? Well, mathematicians decided they should have a meaning, and they even defined the case when you have negative exponents, which is even more ridiculous, or you can take fractions of exponents, and they are actually being used in a lot of disciplines where they use math, like say economy, science, or engineering. They're used everywhere. Even in your banking system, they use the fractional powers. So it is actually a very useful thing to do. But who came up with this? Well, I don't know who came up with this, but that person, whoever it is, they were defining this in a consistent way to all the previous rules. So let me explain why. So take this rule C, take this rule right here, and I'm going to use that with m being 1 and n being 1. Okay? Since this is always true, it must be true when you have m as 1 and n as 1 too, right? So let's say you have a to the 1, we decided that m should be 1, right? And n should also be 1. And the right side would say a to the first power minus 1. Okay? Then if you look at this right side, what is this? A to the 1 minus 1 is 0, right? So that's a to the 0th power. On the other hand, what's a to the first power divided by a to the first power? That's a divided by a, which is 1, because anything divided by itself is 1, isn't it? 3 divided by 3 is 1. 5 divided by 5 is 1, so it's always 1. And therefore, we have established that a to the 0th power is equal to 1 if you allow 0th power to exist. So here's the thing. If you allow 0th power to exist and you want to be consistent with the previous rules that you have, the only possible choice is that you're forced to say that a to the 0th power is 1. And having a to the 0th power is 1 will make it a lot easier to use these other rules, because you don't have to give a second thought, what if this is 0, right? You can just still use these rules without any hesitation, because it still works with a equal to 0. I mean the power exponent equal to 0. Okay, now the next one I want to show you is, what about the negative powers? I mentioned this, right? The negative powers is 1 over, let me use n instead of m. So negative n would be a to the n. Now why is this true? In this case, we're just going to use the same rule again with m equals to 0. So if I use this same rule with m equals to 0, then you get a to the 0th power over a to the n equals to a to the 0 minus n. And again, we see that the right side is a to the negative n, which we are looking for, and the left side, since a to the 0th power is 1, this is just simply 1 over a to the n. Okay? So that's how you establish that this is true. Okay? So even negative exponents make sense. But let's think about this. What does it mean to multiply to negative 3 times? Well, think of it like this. What's the opposite of multiplication? It's division, right? So in a sense, you're dividing by 2 once, twice, and 3 times. And that's why this is equal to 1 over 2 to the third power. So not only our previous rules force us to say that a to the negative n is 1 over a to the n, there is a way to understand this, saying that since opposite of multiplication is division, you can think of it as the reciprocal. Okay, so negative powers gives you the reciprocal of that power. That's what this theorem, this rule is saying, and I'm saying that that also has a nice meaning to it. Okay, so the last one I want to say is the fractional powers, a to the m over n. What does that mean? Well, that means it's nth root of a to the m. And this one requires a little bit more explaining to do. So it's like this. If you have 2 to the 2/3 power, if you wanted to know what this means, an easy way to do this would be take the cube of it. Then rule number b applies, right? Which says if you have a number outside the parentheses, they multiply. So this gets multiplied, and 2/3 times 3, 3 cancels, and you end up with 2 to the 2nd power, right? So 2 over 3 times 3, they cancel, and it gives you 2, right? All right. So using that, we have this being 2 squared, and if you have something cubed equals to 2 squared, that means that this x is a cube root of 2 squared, right? So you have that this thing, since it satisfies this equation, you can say that 2 to the 2/3 power equals the cube root of 2 squared. So that was a little bit more convoluted, complicated reasoning, but to summarize, all I'm saying is that it should be a way to make the previous rule still hold, even if you extend the meaning of exponents to fractional powers.